You're what? A second year? What's your program?
The third year physics spec, sort of ish.
Third year physics spec. Okay, good enough. That's good enough. And you're talking about what you about
My
your
research, well, about
like
TRIUMF and my research.
TRIUMF and your research this summer?
Last year. Yeah.
Oh, I should mute myself. Okay.
Poll.
Yes. All right. Thank you everyone for coming. Welcome to the fourth, I think at this point, PhySU Colloquium this year and ever. I would like to welcome Aryan. He's a third year physics specialist student here to talk about what he did this summer at TRIUMF and a bit more about TRIUMF itself. So welcome.
Great. Well, thank you everyone for being here. It's I'm so excited to share all this with you and the slow motion train wreck. So without further ado, yeah, let's begin with Hyperfine Spectroscopy for Dummies. And I promise I am the only dummy in the room today. So that's because of how I've scoped this talk, essentially. Basically, so the Hyperfine Spectroscopy, that is the work I did last year working at TRIUMF, which is Canada's Particle Accelerator Center. I worked there from January to August, and that's going to occupy more or less the back half of the talk. But before that, I'm going to talk about TRIUMF as a whole and the science they do there and all the cool stuff, because I think, well, not enough people know that Canada has a National Particle Accelerator Center. I think that's really cool, and it's worth talking about. I mean, I didn't even know that existed until a few months before I started there, and I didn't know of all the interesting things they did until I got there. So I want to share some of that. It's more of a survey overview, so we're not going to go too deep into things in the first half. If I'm talking too fast or if anything's unclear, please just ask questions. I'd rather go into more detail on fewer things. So yeah, there's a lot, so brace yourselves. And let's begin. Welcome to TRIUMF. So, all right, you can see here, so TRIUMF is Canada's Particle Accelerator Center. And if there's one thing you learned from the talk, I want it to be that sentence, because again, it's cool that Canada has a particle accelerator. So over here, so this is the TRIUMF, it's in Vancouver, so this is the TRIUMF campus, right in the edge of this nice forest. Up the road is the University of British Columbia campus, and off is the gorgeous Coast Mountains. It's a very nice location for a particle accelerator. So TRIUMF was founded in 1968 as the Tri-University Maison facility. Tri-University because there were 3 Vancouver area universities that made it up, and Maison facility because they made mesons, which are a type of particle. There are now 21 universities in the consortium, and they don't make mesons anymore, so we just call it TRIUMF. Now, there are about 600 staff at the site, and that includes many visitors, because TRIUMF is a user facility. Essentially, if you're a scientist anywhere in the world, you can write a proposal for an experiment you want to do at TRIUMF and then come and run it. So there are a lot of visitors, and it's got about a $225 million operating budget over 5 years, which is not enough in my opinion. I might be biased. But let's get to the headline item, which is that TRIUMF has the world's largest cyclotron, which is Guinness World Record certified. It's a type of particle accelerator that we'll talk about. But the idea is that it accelerates negative hydrogen ions to 75% the speed of light. That's an energy of 520 mega electron volts. So for comparison, the LHC achieves energies in the tera electron volts, so it's a much more low energy accelerator, but it's perfect for what we needed to do, which I'll talk about. It's also not the most energetic cyclotron. It's a close second, but it is the largest. It's an 18-meter diameter machine, and it's got a bunch of magnets which each weigh 4,000 tons, and they were so big that they actually needed to be built by shipbuilders. And that company actually donated a captain's wheel that's very proudly on display in the TRIUMF offices. So this is inside of the cyclotron chamber, so it's all encased by concrete to protect against radiation. And sort of this is more or less the machine. It's like the actual acceleration happens like inside here. You can't really see it. This whole thing is the lid of the cyclotron, which physically gets raised and lowered so that we can do maintenance on it. So these are some maintenance workers who've suited up in radiation suits, and they're inside the actual chamber where the radioactive beam would be. It's not a lot of space, certainly. And then here's a bit more underneath the cyclotron. So these like yellowish things are the magnets. Then they're supported, of course, by all these supports that also provide electricity. This cyclotron is very energy hungry, and it makes TRIUMF the biggest energy consumer in British Columbia. All right, so how do cyclotrons work? And okay, the basic idea, we want to accelerate particles to go very fast. And we can do this with electric fields. they can do work in particles, increase their kinetic energy. But the amount by which they can do that is proportional to their strength. We can only make electric fields so high just by sheer mechanical constraints and safety. So, but we also know that if you have a charged particle in a uniform magnetic field, it'll undergo circular motion. So we can combine these ideas. In the center of the cyclotron, we unleash a charged particle with some velocity. The magnetic field will curve it around so that it goes over this thing called D's, which is essentially a small gap through which we put a very strong electric field, as strong as we can reasonably make it. And so it gets accelerated a bit, and that'll cause it to spiral outward in radius. And then the magnetic field gets it to curve in again, and then it accelerates again. So it keeps looping around through the cyclotron, each time passing over that electric field and gaining some energy. So as it loops out and out and out, it gains more energy up till its like outermost radius, where it has that 520 MeV. And like classically, that cyclotron frequency is constant, so the amount of time it takes to make a full revolution doesn't depend on its energy or its radius. But the protons themselves are relativistic, so when we compensate for that, we realize that the magnetic field needs to become larger as the radius as you go further out in the cyclotron. So that leads to this characteristic shape for the magnets, which are, it's a very interesting shape. Obviously, a lot of work went into figuring this out, and this is now incorporated into the TRIUMF logo. And so this is when they're christening a cyclotron. Each of these is an individual person, so that gives you a bit of a scale for the machine. All right, so that's what happens inside the cyclotron. But then how do we get things in and out? So and that's where the beamlines come in. So we insert H- ions. I believe they're created through some gas discharge process. The details aren't too important. But it's this is behind the cyclotron, the ion source. They would then be inserted into the center, and then we have extractors inside the cyclotron that can extract the H- beam from any point inside, so that we can get various different levels of energy, because the energy depends on where in the cyclotron you are. So like into these concrete blocks, there would be some extraction mechanism, which has some graphite that would strip off the electrons from the H-, making it a proton beam. And then the proton beam goes out through these arms. There are multiple extraction arms, and then onto the beam lines. So you have the cyclotron, you have beam lines that then go into the meson hall, where you have experiments, and then one that goes under the surface to the isotope separator and accelerator center. So why do we want this though? Essentially for rare isotope production. The idea is very simple. You have really fast protons and you smash them into target material, and that makes nuclear reactions. And there's a whole theory of how this works, and little books filled with how TRIUMF produces isotopes, but not really going to get into that. One of the mechanisms, just for illustration though, is a fast proton hits a large nucleus, and the nucleus then shatters into multiple products. That's called spallation. And now the target material, we want to select it so that it produces the specific kind of isotope we want to use in a given experiment. And then there's a whole theory about which target material to use for that. Some are just better at producing certain kinds of isotopes. So one we use often is uranium carbide. So you have some pellets here. These would go inside this little target container. Around here, the proton beam would come in here, collide in here, and then the reaction products would diffuse outwards. And this obviously generates a lot of heat, so we have these cooling fins over which we water cool them. And this whole thing is actually quite small. It's like this big or so. Sure, yeah. What's right? It's just like concentrations essentially. Like it's a small space they're in, and there's like a certain way they can go, so they go outwards. So getting a lot of isotopes produced is really more of an art than a science. In particular, these are short-lived isotopes that we're producing, so they might decay while we're still producing them. And so there's a lot of effort that goes in by a lot of very smart people to ensure that we get enough isotopes for our beam. All right, so we've produced it, and so just for an idea here, here's the proton beam going underneath the surface. I believe here shows the target chamber where that actual reaction happens. And then there are various experiments in the isotope separator and accelerator, the ISAC complex, that we want to deliver to. And so for just another view, this is the target chamber. So the thing I showed on the last slide, it would go around here or so, and then this is all encased in a lot of concrete for radiation. So basically, the isotope production is messy, right? It produces a lot of different things, and we want just one specific isotope. So this would be very easy if everything was ions, because then we can use electric fields to accelerate them away from away into the experiment, and also use them for mass separation. So we know the mass of the isotope we want, and so we could apply an appropriate deflection such that the mass we want is the only one that gets to the beam. So basically, we need to produce ions, and there are multiple methods: lasers, hot surfaces, plasma chambers. I'm a bit biased towards lasers. There are two methods. So for lasers specifically, there's non-resonant ionization, where you essentially just dump a whole bunch of laser light onto an atomic beam and hope that's enough energy to free the electrons. Or you have resonant ionization, where you actually tune your laser frequencies to these exact transitions that will bring an electron up to its ionization potential. And the great thing about this is that it's element selective. So, if you tune to one isotope's ionization potential, then, that frequency of light, it probably won't interact with the other isotopes. So your ion beam is exactly the isotope you want. All right, I'm going to digress a bit to talk about radiation, because TRIUMF does produce a lot of it. So this is one of the control rooms where the operators steer the beam, and they're mostly good at it, but it's a complex system, and sometimes you get what are called beam spills, which are essentially where your charged particles impinge on, say, the sides of the cyclotron and make it radioactive. And of course, there's the production of rare isotopes, which is intensely radioactive. But it's really not much to worry about if you're just working at TRIUMF, because TRIUMF cares a lot about safety, and all of this stuff is shielded by layers of concrete and whatnot, and people are very well isolated from it. One of the things TRIUMF has very well developed is remote handling procedures. So essentially, if you're trying to exchange a new, switch out target materials in the target station, you can use these robotic arms to change it out instead. And you'll be on the other side of this heavy metal, so you'll be completely shielded from the radiation. Here's my friend having a bit too much fun with the robot arm. And yeah, and then there's external containment. So this is the Meson Hall, where a bunch of experiments are, and all of these yellow blocks is like a huge block of concrete that captures all of the radiation that comes off the beam lines and the cyclotron. And so if you're just walking around, you're not going to be exposed at all. So if you're smart about radiation, it's really not much of a threat. You don't have to worry about it too much. And TRIUMF is regulated by the Canadian Nuclear Safety Commission. So there are limits on how much radiation workers can be exposed to and how much can be output to the environment. So I believe here is the regulatory limit, and here is how much TRIUMF outputs to the environment. So it's very safe. There's a thriving forest on the other side of the fence, so that's proof of how safe it is. And I'll tell you in 1 second. But a fun fact that I learned during my radiation training course there is like a way of quantifying risk as the expected value it takes off your life. So working at TRIUMF for your whole career is about 40 days off your life. The riskiest thing they told us about was being a single male, which takes over 3,000 days off your life. So I'll let y'all think about that. Yes. So if you're on site, you're always wearing a radiation badge that tracks it. And so just working in my office, I never got exposed to any radiation. I did, I toured some of the cyclotron halls and stuff. That was maybe in the microsieverts, I believe, which is, the yearly limit to an ordinary civilian is 1 millisievert, which itself is all very non-problematic. So I'm fine. All right. So we've made rare isotopes, we've ionized them. Now we have to deliver them to experiments. So the ISAC hall is where the big experiments are. ISAC 1 is low energy stuff. So down here, this is a bit outdated. There's some new experiments. And then ISAC 2 is high energy. So your beam would go through here. It goes through another accelerator. This one's just a linear type, so some electromagnetic fields increase energy to kiloelectron volts, something like that. And they get delivered to high energy experiments. And so there's a whole zoo of acronyms for these experiments that are very contrived and yet somehow still make sense. You can ask me about them after. But essentially, if you're a scientist at TRIUMF, you're managing 1 or 2 or maybe a small handful of experiments. And so, but there's a bunch of these experiments, and there's only 1 beam provided to this whole facility. So what you're doing is writing a proposal for beam time, trying to say why you need more data and why you should get beam to run your experiment. And if the steering committee approves that, then maybe you get a week out of the year of beam time, through which the cyclotron is running 24/7. So you have your grad students working the night shifts and getting as much data as possible to use for the upcoming year. All right, so so this is a view of the experimental hall. It's kind of a jumbled mess. And then this is a diagram of one of the experiments. My point in showing this is just to show that each experiment is a very complex entity in its own right that could occupy a full presentation, and no one person can know all about them. So there's just endless complexity here. There's so much that goes on, and I just want to like get a little picture of that. All right, so TRIUMF is about nuclear science. Well, why do we care? Basically because the underlying theory used to describe protons and neutrons, quantum chromodynamics, is too hard to actually describe the nucleus. And so we use things like the nuclear shell model instead, which is very similar to the electron shell model in that protons and neutrons each occupy discrete energy levels and they, emit some angular momentum states. And just like with electrons, a full energy shell makes a nucleus very stable. So this is where you get your nuclear magic numbers. So, if you have that many protons or neutrons, you're a very stable nucleus. And if you have that many of both, so if you have full shells for both, then you are doubly magic and awesome. So the model here, it's something like a harmonic oscillator, but with some deformations due to interactions between the nucleons. The predictions for this are not great, so we need a lot of input from the actual experiments, empirical parameters, to help us make better predictions, essentially. And so much of what TRIUMF does is nuclear structure phenomenology, where essentially these theories, the shell model, predicts very measurable things like the mass of a nucleus, its charge radius, or whatever. These are things that we measure at TRIUMF, and then based on what we get, we can make improvements to the theory so that we ultimately get better predictions and a better understanding of the nucleus. So I'm going to talk about a couple specific experiments that I just thought are interesting that highlight some of the science. So there's the gamma ray spectroscopy group, which essentially they detect the gamma rays and neutrons that are emitted when radioactive nuclei decay or when they go from a nuclear excited state to the nuclear ground state. So on the right here is the Griffin detector opened up. So you'd have your radioactive beam coming in here and it gets trapped here, this little black box where it would decay. And then these red metallic things are germanium detectors, which would detect the gamma decays. And when this is closed up, it surrounds the entire decay chamber in a full 360 view. So we detect all the gamma rays that are emitted. And then the thing on the bottom left is a detector array, but it's for neutrons. And so the idea of these experiments is to study how the nuclear properties evolve with changing proton and neutron number. And that should tell us a bit about, help us better understand the nucleus, essentially. This group also has excellent cable management practices, as you can see from that picture there. All right. So this is the chart of nuclides, which is this poster is on basically every wall at TRIUMF. It's our periodic table, but it's better. So it's all the known nuclei as a function of proton and neutron number. So the blacks are the stable nuclei, and all these other dots are unstable ones. What's interesting are these blue and green lines, which are known as the drip lines. Essentially, if you have more protons than allowed by the blue line, or more neutrons than allowed by the green line, your nucleus just straight up cannot exist. And so these are the limits of nuclear existence, as they're called. Now, they're not actually that well known, so one of the goals of TRIUMF is to make lots of different isotopes and explore the limits of these existence, figure out where the drip lines actually are. And, TRIUMF can make a decent, a very large fraction of those isotopes known to exist. And so, it's a very cool thing we're able to do. So the yellow are the isotopes for which we've at least measured its mass. I think, and evidently the proton drip line needs to be updated. So yes. All right. Another cool application is in nuclear astrophysics. So basically, we want to know where the heavy elements in the universe, those beyond iron, came from. One interesting point of evidence here is that iron. So we look out into the cosmos and we see very old stars that are poor in iron, but they contain heavy elements like uranium. So we want to know, how those could have formed. And the idea really is neutron capture processes, where your nucleus, it gains a neutron, and that neutron eventually beta decays, so you then gain a proton. And so you can see here, just by doing neutron capture beta decay, neutron capture beta decay, you can kind of zigzag your way up the chart of nuclides and create a remarkable amount of different isotopes. Now, there are two ways this happens. There's the slow or S process, which happens over thousands of years, and essentially a nucleus would gain a neutron, it would then beta decay, and that would be a more stable isotope. But then there's also the rapid process, which is needed, essentially means you gain a lot of neutrons before you can beta decay. And that is needed to explain some of the abundance of neutron heavy isotopes in the universe. This would happen in fast moving scenarios where there's a high neutron flux, so neutron star mergers essentially. The cool thing here is that we can simulate some of these reactions by shooting high energy isotopes into hydrogen gas. This is what the Dragon experiment does. And then there are also lots of people running simulations of nuclear processes, and their simulations are only as good as the data we have about beta decay lifetimes, about reaction rates. So providing more information from these experiments is critical to understanding the origin of the elements. And there are other applications to fundamental symmetries in the universe, to material science. I don't have time to talk about those, but you can ask me after. All right, so let's talk about perhaps the most important application, which is nuclear medicine, which it's really in two different sectors. There's medical imaging and therapies. So in imaging, we have positron emission tomography. The idea is essentially you bind a radioactive isotope to some chemical compound that you then inject into the body, and that gets used up in the body somehow through some natural process. And the idea is if you surround yourself with a bunch of gamma ray detectors while this is happening, the isotopes will decay and you can detect their decays. So you can figure out where this isotope is being used, how it's being used. So it's a very functional level view of the biological processes that are happening in the body. It can also help detect cancers. And onto that, then there's radiotherapy. Before I do that. So this is a PET scan, I believe, for iodine. So you can see it, I believe, collecting here in the thyroid. Iodine naturally does that. And it actually has a cool application to radiotherapy. Is basically short-lived isotopes, if they're right next to a tumor, they'll decay and the radiation will kill that tumor. And this is a good way of directly attacking tumors, especially if there's like a place where they build up. So if you have thyroid cancer, iodine naturally collects in the thyroid. So if you insert some radioactive iodine, then it can be used to effectively kill that tumor. And we're always looking for new cancer therapies. Radiotherapies are not. The point is, cancer is a complex thing. And the more avenues we have to attack it, the better our overall cure rates would be. There is an interesting digression, though, is that instead of doing all this, you could just shoot proton beams directly into your eyes, which is what they did at the proton therapy facility at TRIUMF, which operated some time ago. Basically, they just take an energetic beam directly from the cyclotron, shoot it into someone's eye, and cure their eye cancers. Now, medical isotope production is... Oh, sorry, did you have a question? Yeah. But that's what they told me anyways. Yes. That's also what they told me. So medical isotope production, it's huge in demand across the globe, and so lots of large hospitals have their smaller cyclotrons where they produce it. But UBC Hospital gets the best. So over at TRIUMF, we produce isotopes, and then it goes underground in this vacuum chamber straight to UBC Hospital where it can be used. That's the rabbit line that was famously featured in the Tom Scott video. And all right, so that's what TRIUMF does currently. Let's look a bit to the future now. So I mentioned that all the ISAC experiments currently get one beam. The idea with Ariel is to triple the number of active beams and thus triple the amount of science we can do. By the way, don't ask me where the E went in the acronym. But so hopefully the goal for this is to be online by 2026. And so you can see here on the left is part of the isotope beamline that's underneath Ariel, and then this is a nice shiny building on the outside and the glorious Vancouver rain. And so the thing that powers Ariel is actually not the cyclotron, it's like the exact opposite. It's a linear accelerator that accelerates electrons. And it's lower energy, but because electrons are light, they can go very, very close to the speed of light. And we can have a very intense beam with them. And the idea is that this electron beam would be shot, and in the target station in Ariel, they would get rapidly deaccelerated, which would produce gamma rays that induce nuclear reactions. And so the source for the electrons is 1,000-degree tungsten, which is hidden in this Faraday cage in this picture. And then that electron beam gets shooted through some accelerator modules, which is just electric and magnetic fields again. And yeah, and then they get shot off. And so this is the whole electron hull. It's just a funny picture to me because you wonder what a particle accelerator looks like, and then you actually see one and it's just a mechanical monstrosity. All right, that's TRIUMF. So this is just as an overview, this is a map of the site. Everything here is the main accelerator building. So we saw the inside of the cyclotron vault, the electron vault, the Meson hall is the stuff with the concrete and experiments, a bunch of experiments over at ISAC, Ariel's a new building. And then there's some like various other buildings that provide engineering support and whatnot to the site. And then these are all the beamlines we have. If you'll notice onto the right here, there's some smaller cyclotrons as well that are focused on medical isotope production. Now I want to talk about isotope production in its global context, because there's a large demand for it. So you can see there are a lot of facilities around the world that can produce rare isotopes. But TRIUMF is special in that it's among a small handful that can produce a wide variety of different isotopes. So, it's up there with a facility at Michigan State, at CERN in Japan, and one in Germany, and maybe one or two more that I'm missing, that can produce a large variety of different isotopes and is really doing general studies into nuclear science and medicine. And so it's a really cool thing that Canada puts the investment into this to supporting this research. Fun quote is when the cyclotron was christened, Pierre Trudeau was prime minister, and he said, "I don't know what a cyclotron is, but I'm sure glad Canada has one." Well, now you know what a cyclotron is, and you can be glad that Canada has one. All right, so that's the first half of the talk. That's the overview of TRIUMF. Now we're going to talk about my group and my project. And have some water. All right, so Trialis, TRIUMF resonant ionization laser ion source. I told you these get contrived. So we have about 5 laser labs across the site, including one very nice new one. And the reason the group exists is to provide ionization services for a variety of isotopes, and we can do quite a lot. So this is our group leader, Jens Lassen, working on a laser table, which is his favorite thing in the world. And he likes to joke that we are the smallest group doing the hardest work. But we do that, and then we also carry out spectroscopy studies and other atomic physics things in our spare time. And so this is the laser setup I was working on last summer. This is a diode laser that outputs a constant 532 nanometers green light that gets pumped into the inside of this laser cavity, bounces around, goes through this titanium sapphire crystal, and excites the atoms in that crystal, which as they get de-excited emit this red light that then goes off into whatever application you need it to go to. And so this is a titanium sapphire TISAT laser. The really cool thing about these is that by controlling, so this is, I believe, the Fabry Perot interferometer on it. By controlling the size of that, you can control the wavelength of light that gets emitted. So say if you're trying to provide ionization for a whole bunch of different isotopes with their own frequencies, it's really good because you can just turn some knobs and get the correct wavelength of light that you need. All right, so onto my project. So first we have to talk about nuclear magnetic resonance. Basically, your nucleus has some net spin. And if you apply an external magnetic field, they will roughly align in that direction. If you then apply, so that's a constant magnetic field. If you apply an oscillating magnetic field on top of that, the spin will precess about that oscillation. And that'll emit some electromagnetic signal. So the frequency of that precession, it depends on what the magnetic field is like locally to that isotope. And so it generates some electromagnetic signal that you can then detect. That tells you about the magnetic field structure of your whatever sample you're studying, and that can tell you a lot about it. And this is used, it has various biological applications for studying living tissues and whatnot. Now, unfortunately, you need quite a lot of, so the idea, like in a TRIUMF context, you would shoot whatever isotope you have into some sample and then do NMR within that sample. The problem is that you need a lot of isotope present to get a sufficient signal here. And so the idea, and the problem is that there are certain isotopes like actinium, which are in very low production, like less than 10,000 counts of them per second. And so we can't do NMR with them. But it's a problem because actinium is a potential radiotherapy. It could be used, say, as a potential cure for cancer. We would insert actinium into a tumor cell and see how that responds. So to do that, we can't use NMR. Instead, we use beta NMR. It's the same principle, but using beta decays instead. So the beta decay is also aligned in the spin direction. And so using that, it would tell us roughly aligned in the spin direction. And so with that, it would tell us what the magnetic field is like locally. And we can detect beta decays very well, so it's a much more sensitive technique. But for that, we already need the incoming nuclei to be spin polarized in one direction relative to each other, about greater than 80%. So we need to spin polarize our nuclei. Now, how do we do that? Well, spin coupling. All right, brace yourselves. So we're using this picture of the atom where we have the proton at the center and the electron orbiting about. Now, the proton has some intrinsic spin, which you can think of as a small loop of current. Don't ask me why. And that loop of current produces a magnetic dipole, which is proportional to the spin and a whole bunch of stuff, as well as GP, the gyromagnetic ratio, which is essentially the proportionality constant for this system. And now that gyromagnetic ratio is very small. And so that magnetic dipole is very small. Like this is an absurdly small magnetic dipole. But still, it'll produce a magnetic field that the electron will see. And if it's an ideal dipole, it'll look something like this. Now, through that interaction, there's some energy. So we can have a Hamiltonian for it, which is just the dipole moment of the electron, dot product with the field it experiences. And again, the electron has some spin, so it has a dipole moment. And so we can let Griffiths evaluate this Hamiltonian, and we get this small monstrosity that I will not attempt to explain. But basically, so this, it's a small interaction. You might call it fine. I'm actually going to call it hyperfine for reasons I'll be clear in a sec. But so this is the hyperfine interaction. It's not the only thing though, right? The Hamiltonian is our total energy in the quantum system. And so we need to have the kinetic energy of the electron on the left, the potential energy due to the attraction of the proton in the middle. So that's the stuff you'd solve. That's what you do when you solve hydrogen in a first quantum course. And then we're adding on this hyperfine interaction. And so we want to solve the Schrodinger equation that says that the Hamiltonian operating on this stationary state of the wave function is equal to the energy times the wave function. The point is, I don't need to tell you that this is obviously impossible with the thing I just wrote down. So instead, we resort to perturbation theory, noting that the hyperfine interaction is very small, and especially compared to the Coulomb interaction, which we know is strong, we can essentially write the total Hamiltonian as that original, just like simple hydrogen Hamiltonian plus a small perturbation, the hyperfine Hamiltonian, which is parameterized by lambda. And so we can expand then the Schrodinger equation. We can write the wave function and the energies as power series and lambda. And once again, letting Griffiths do the work, we find the most important equation in quantum mechanics, which essentially says that the energies are perturbed by this new Hamiltonian. So like the energy level changes, and the amount that it changes is equal to the average value of the perturbing Hamiltonian in the original ground state. So the point is the energies are changed by the Hamiltonian. And when we evaluate this, we find something interesting for this hyperfine interaction, is that what used to be one energy level gets split into two. Specifically, if the nuclear and electron spins are aligned, it becomes this top thing, and if they're misaligned, it becomes this bottom thing. So that is the hyperfine splitting. This one energy level is split into two. Now, it's a very small difference. It corresponds to a transition frequency of about 1400 megahertz, and that is a wavelength of light about 21 centimeters. Now, as it happens, there's a lot of light or hydrogen in the universe, and it's constantly transitioning in hyperfine states. So there's a lot of 21 centimeter radiation that you can detect if you have the right radio telescope, which is quite interesting. But I mean, for our purposes, the point is that it looks something like this. Your original energy level, it's now split. And this, again, it's an extremely small effect. There's actually another splitting due to the relativistic nature of the electron and other electromagnetic interactions. That's fine splitting, that's bigger. It's not really relevant. The important thing is that we can drive this hyperfine transition with a laser, and because it's related to the nuclear spin, we can use that to orient the nuclear spin of our entire beam. Small complications, though. So we just did this for hydrogen. Yes. Well, that fine splitting doesn't couple to the nuclear spin. That's the thing. Yeah. So it only gets worse from here, because in multi-electron atoms, you have this interaction term that suddenly means the potential of the outermost electron also depends on its orientation within the atom, not just its distance from the nucleus. So that's very complicated. Now, this is a hyperfine splitting spectrum for lithium. And two really takeaways here are that the hyperfine splittings, they're all on the order of megahertz. So this is small compared to these principal differences. And again, it's more complicated. It's not something we could easily predict. And so that gets us to the name of this talk, which is Hyperfine Spectroscopy, and why we need to do it. So first, we begin with classical spectroscopy. Basically, you have your laser, you shoot it at a beam of atoms. If you're on a transition frequency, you excite the electrons and they de-excite, and they'll emit some light. So you sweep your laser frequency with your titanium sapphire laser, and you detect the light that's emitted as a function of frequency. And if you detect a lot of light, you know you've hit a transition. So that's what this hyperfine spectrum is. You look, you sweep as frequency, and then you detect your counts, your high counts, your transitions, and everything else is noise. The problem is that we mentioned these isotopes, or the isotopes we want to study, are already low production. And light detectors are just too noisy. Even if you put them in pitch blackness, they would detect something that would drown out any signal from, say, actinium. So now what we want to do is, well, we know ion detectors are very precise. They can detect individual ions, they have a low error rate. So if we can somehow drive hyperfine transitions that produce ions, we're cooking again. So this is the scheme. As before, we frequency sweep a laser to drive a hyperfine transition. We then excite from that transition to what's called a Rydberg state and make a Rydberg atom. So you can see here the principal energy levels of various atoms. They converge to some ionization potential, but really your like n number can get as large as you want it to be. And this just keeps getting incrementally higher and higher in energy. So above n equals 10 or so is called a Rydberg state, making it a Rydberg atom. Those are like the real excite, and those are like excited, loosely coupled electrons. And so you can then apply an electric field to a Rydberg atom, and because it's so loosely coupled, that electron will just become free. And so the idea here is that this is your normal Coulombic potential, but then when you apply an electric field, it deforms that potential, so your like high-lying electrons are just free. And this equation tells us the electric field strength we need. It becomes practical for about n equals 10 or so. So yeah, and then so we now need to make an actual design, a field ionizer. So there's some design priorities. We want to, so in the beam, there will always be collisions among the particles. And so they will be producing ions all over the place. We only want the ions that we produce via field ionization, because those are the ones that we know were excited in a hyperfine transition. So we want to get rid of all other ions. And on that same note, we want to impart ions with an energy signature, which I'll try to explain in a bit. So, okay, now we go to our first design, which is courtesy of a German master's student in the 90s. This is like the prototype. And essentially, it's a series of high voltage electrodes. This is the cross-sectional schematic. This is what it looks like built. And you can see we like climb to 12.5 kilovolts, drop suddenly, and then go back to ground. And so there are really three regions of note here. The first, and you'll see this pattern for the other designs we look at, but the first region or so is the deflection region, where the idea is that any incoming ions would just be deflected off by the transverse fields. Then in here, in the sudden drop, is the high electric field that will produce the ions. And then we just go up to ground. That's what's called the post-acceleration region, or just where ions are then shot out the back. Okay, so I modeled this in our finite element software, and basically we want to find the potential everywhere. That amounts to solving Laplace's equation. So what we do is discretize space and then approximate the potential all over the place. And this is what we get. Like, these are the regions of high potential, these are low, and you can kind of see how it evolves as the beam would see it. Now, some important things. The strength of the field determines where the ions are produced. However, when an ion is produced, it starts at a given potential, and then it moves through the potential through the rest of the ionizer. And so the potential at which it's created, it essentially imparts it with a specific energy that we can then detect. Now, the idea is if we want all of the ions that are produced at a certain field strength to have the same, to be at the same potential, because that means they'll have the same energy. And so when we apply deflection based on energy, we will only get the ions we want to see, because essentially, if we have a one-to-one mapping between electric field and electric potential, we can then find out the energy of the ions created by the field ionization, and then deflect all of the ions that we have at the end of our beam just the right amount. So the ones with the energy we want are the ones we end up detecting. And so the point is to have a one-to-one mapping between electric field and potential, if at all possible. And so you can see this design is not too great at it. So here's the general idea. The potential increases, decreases, and this is roughly where you get your localized high electric field. The dashed is slightly off the central axis of the ionizer. The solid is on its axis. And you can see that there's quite a big difference in the fields on and off axis. And you can do another analysis of this. But essentially, these are the differences. So several kilovolts of potential difference for some of these like critical field strengths, which is definitely not good. But to the students' credit, this is only the prototype. So then they spent some time working and devised a new design based on the original, but also using some good intuition about the physics here, and probably just some good creativity, and came up with this. So this is what it looks like built out, and this is the schematic. First thing, so the first region, the deflecting electrodes are now angular, and so that idea there is that they create stronger transverse fields that deflect ions, and in simulations I've ran, they work very well. And then you have this ionization bit, which is very weird. But the idea here is that you can see what these equipotential lines look like, these arcs from electrode to electrode. The point is to mimic the field of a point charge, because the field, the like equifield and equipotential lines for a point charge are the same. So the point is, if you were ionized at a certain field, you experience the same potential, and thus you have the same final energy. And then we can uniquely identify you as the ions we want. And so that's the goal here. And it does work quite well. You can see, first of all, there's a much steeper drop in potential, so you get a much sharper and more localized high electric field, and they track more closely on and off axis. And once again, you can see that here, especially in like the key electric field strengths we want, like the middle region here, there's a very small potential spread. So it's a good design, but we only want the best. So that's where we jump to the future a bit, a new design that came out of CERN a few years ago. It's the same 3 segments, but they're implemented very differently. So you still have the deflecting plates, but now they're just flat plates that build in potential. The ionization region is very interesting. It's 3 wire grids. And in particular, you note here, this one is at 4 kilovolts, this one is at negative 2 kilovolts, and they're full 4 millimeters apart. So that should harken back to the idea of parallel plate capacitors. If you're an atomic beam, that looks like that's 2 very large plates, both at a uniform potential, and there's a field inside. That field is going to look very uniform for the beam. So that's what's really cool about it. And then you have some lenses that essentially, try to shoot the created ions out back. And so we find here in the simulation that it's a beautiful design. You have a very gradual build-in potential that produces a very low field, and then a very sharp drop that has a very high but very localized in space field. And so ideally, all of the ions there will be created in just that little space. And again, we can see when thinking about the potential spreads that they track very closely. So this is orders of magnitude less potential spread than the other designs, and the one we want to go with. Now, so it has the best energy marking by far. The one problem is that the deflection is a lot more gentle, but that's still something we can work with. So, all right, that's our designs. Now onto the last little segment where we'll talk about building this. So this is our laser spectroscopy beamline, and we want to adapt this ionizer design for use on here. And it's quite a complicated process because we need a way to distribute all the voltages to all the electrodes. It needs to be compatible for a vacuum, so you can't have plastics. It needs to be protected against radiation, and we want it to be relatively easy to make. So we're going to try to use existing parts. So this is a whole summer's worth of work and a whole presentation as well. So I'm going to try do my best to summarize it. But basically, these are my implementation of the deflecting electrodes. So they're a lot bigger because we want it to essentially be a stronger presence for the beam and shield the base plate from seeing the beam. And so this base plate, it provides it has holes for all these to go into, so it's like it keeps everything well spaced. These are ceramic mounts because we can't have conduction between the electrodes and the base plate. And yeah, and now for the mesh mount. So we're gonna have a thin wire grid mesh, and so like the first one, these are all like conducting electrodes. They'll be clamped down here. This is an insulator. The second one will be clamped down here. Another insulator. Third one will be clamped down here, and they'll all be joined together. So this keeps the spacing very, very tight while also keeping everything like everything that needs to be insulated. It's worth noting we can't use normal fasteners for this because they'll conduct between the different electrodes. So, for instance, you might see these little things. These are sleeves for bolts. So this is a little non-conducting bit on which you put a bolt, and then on the other side you put the nut, and that would compress things and make it join together while keeping everything insulated. We also have these little handles that sprout out, and that is where you would attach a wire, bolt it on, and provide the voltage for each electrode. There weren't many details in any of the papers on these about acceleration lenses, so it's essentially just another circular electrode, again, where you can attach wires on whichever end you please. And then we have to put the whole thing together. Again, no normal fasteners because screws are conductive. So instead, we have these ceramic cylinders that essentially push everything together, and then there's interior rods that run through the whole length of everything. And the idea is just use compression to keep the whole thing sturdy and secure. And then our existing laser spectroscopy setup fits in this box. So this thing also fits in this box. And then we mount it with this adjustable base so we can put it wherever we want. And so again, this is a very complex design process. There's a lot that comes into it, and this is just a small fraction of all the struggles that we went through. All right, so where do we go from here? Well, at some point, the TRIUMF machine shop will come through and manufacture this thing, and then we'll install it on our beamline and run tests with it, perhaps with uranium, maybe this year. And of course, then the goal is to do hyperfine spectroscopy on these very low production isotopes and produce spin polarized beams for cutting edge nuclear science and awesome radiotherapies. Maybe at some point I get a paper with this. But the bigger picture is that currently there's really only places at Michigan State and CERN that can do this kind of spectroscopy. And so the goal is for TRIUMF to become one of them. And so this is really where the talk ends. But if you'll indulge me for one more slide, I really enjoyed my time at TRIUMF, and it was really worthwhile, so I want to share some of that. So, this is the student group for the summer. It's like 80 of us or so. If you're ever gonna go work at TRIUMF, do it in the summer, because there's a huge undergrad group that's always up to shenanigans. There's a lot of fun stuff going on at TRIUMF, and Vancouver as a whole is just beautiful. There's a lot of nature to explore. Cyclotron is on, by the way, in case you couldn't tell. And just some other fun pictures we had. So this is the former grad student in my group who wanted to get shaved to learn the nature of his head or something, so we did it on site. TRIUMF branded beer, which sucks, but we had it for the 1 week where it's a conference at TRIUMF, but it's basically an excuse to day drink and game at work. And we have a very competitive volleyball league in the summer, which my team absolutely did not win, but I'm very happy for these guys. But yeah, really awesome experience, and I'm glad I got to share this all with you. So thank you very much.
All right, I guess we'll do a little question answer period. Anyone? Yes? Questions?
That's too much.
Yes. All right, in that case, we'll one. Oh, yes.
Yeah. Yeah.
And repeat the question.
Yeah, okay, so the idea, let me see if I can go back to the right slide. Oh, God. Okay, but the point is, what? Okay. All right, whatever. The cyclotron, it's like, it's got like these weird like angular shapes that kind of like spiral outwards. It's a very non-intuitive weird shape that produces a very weird magnetic field. Basically, I think the idea is that we want to keep the frequency with which the particles revolve around the cyclotron constant, regardless of their energy or their radius in the cyclotron. And so the magnetic field needs to match that. Classically, that happens automatically with a constant magnetic field, but these particles are relativistic. And so we need a changing magnetic field, and the engineers back in the day just calculated it in that such a weird shape would create the magnetic field needed to maintain a constant frequency. Yeah, that's the best I've got, sorry.
Any more questions? All right, I guess let's thank our speaker one more time. And thank you everyone for coming.